Thank you for listening to this video where we're going to go over how to run through a geoneutrino calculation flux software that we're currently calling GEONU. I'm going to start sharing my screen so that you can see the basics of how to go through this software. But first, I want to point out that this code was mostly written in conjunction with a paper that was published in January 2020 by Scott Whitworth, Andre Schrammick, and Bill McDonough. The code was written and published here, but what this version of the software that we're going to review tries to do is make it easier to run and to understand, change, and manipulate the variables in an interactive way. So what you're going to want to do is go to github.com/lskgeo/GeoNu test, because it's the test version of the software, and we are very grateful for you for going through, bashing this, finding bugs, and helping us out here, because it's really going to help us improve the software. Now, if you're familiar with GitHub, you know that you can clone a repository or you can download a repository. There's also a button we have to open in MATLAB online. This code is written in MATLAB, and if you open it in MATLAB online, you don't need to download anything to your desktop. You don't even have to have MATLAB downloaded. You just need to log into a free MATLAB account. However, for demonstration purposes, I'm going to use a version that's on my desktop because it runs faster on my desktop due to limited internet connection speed. Now, once you have this downloaded and you open MATLAB, what you want to do is double-click on the project file. Your MATLAB setup might look slightly different from mine. I have it in dark mode right now, and I've arranged my windows how I like. Yours might look different. You might have a couple of different files here as well, as this is a master version that I'm working on. But don't worry, you'll have all the files you need on the file path if you double-click on this geoneutrino flux calculations.prj file. So that is the project file that launches everything. I just clicked that, and what I had before, there we go, is I have this main menu that pops up. I have a couple of options for interacting with the software. I can do a full software walkthrough. I can use a short calculator form that has all of the calculations I need, but doesn't really have any explanations, figures, or rich text. So this is if I just want to run the calculation. And we're still working on the different sections and buttons of this menu, so we're going to just hop into the software full walkthrough version. This is what I recommend doing for the first time you use this software. So I clicked that button, and it opened up this live notebook. Let me just go like this to make it a little bit bigger and easier to see my different windows. And you should see this Introduction to Geoneutrino Flux Calculations script. Now, you'll see, as I said, it's a dark mode on mine. Might be a couple of different colors, but don't worry about it. It'll be the same text for everyone, even if your MATLAB is set up a little differently. In the beginning, we review what are geoneutrinos, right? We want this script to be understandable to the general scientists who might not know what geoneutrinos are or how we detect them. Throughout the script, if you want to learn more, you can click on any of the hyperlinks, you can read the rich text in each section, and you can read any of the papers that are associated with it as well. The main crux of this is that we want to figure out what the geoneutrino flux signal is from the lithosphere, the mantle, and the core. The core actually has no uranium or thorium in it, or negligible amounts, so this is 0. So we want to know the total geoneutrino flux from the mantle and the lithosphere. What geoneutrino detectors measure is as total geoneutrino flux, but as geologists, we want to know the amount of geoneutrinos coming from the mantle, the heat-producing elements in the mantle, since it's the largest silicate reservoir on Earth, and it can tell us a lot about how Earth formed and how it's going to develop in the future. However, as you guys know, there's no directional information associated with the geoneutrinos that we measure in the detector. So if we want to know what's in the mantle, we have to subtract out what we expect the geoneutrino signal to be from the lithosphere, or rather the crust plus the rigid part of the mantle, if we want to figure out the rest of the mantle. All of this text reviews that and the different calculations that are involved in calculating a geoneutrino flux. And we also review why it's important, why we need to know about heat-producing elements in Earth. The actual software itself starts after the table of contents. They said this is hyperlinked, and I want to skip down to step 1. Now, step 1 is where we initialize and define our model space. So this is where we tell the code which geoneutrino detector we want to look at and what different parameters we want to start with. You'll see again, there's some links, there's some figures to look at, and then you'll encounter the very first line of code where you get to choose which detector you are interested in. However, maybe I'm not interested in reading the code itself. I just want to run these calculations and test different parameters. So I can actually go to my sidebar and click the Hide Code button. And then what I will see, give it a minute, my computer is lagging just a bit because I have this recording going along with a couple of other things open. There we go. Sorry about that. Computer's trying its best. And what happens is the code disappears, and instead you will just see the rich text and the controls we have. You can also change the view if you go up to your tool strip up here, go under View, and you can choose to have the output of the code right below it, as we just did, or we can once again go back and hide the code. What I'm going to do right now to save time on this recording is I'm going to go up to the tool strip and hit this big Run Everything button. This is going to run every part of the code from start to finish. And I'm going to set it to run now because it takes 3 or 4 minutes, and we'll explain why. And so this can run in the background while we go and we look at which parameters I've chosen and how to change them. And then hopefully by the time we get through that explanation, our run will be done and you can see the results. Go up here and click Run. In MATLAB, there's a couple of different ways to run codes. If you're familiar with it, great. You can run all sections, you can run some sections. I recommend just hitting this big green Run button. And now this will go in the background as we continue on. All right, so we can change which detector we want to look at. There are 6 detectors currently built into this. Say I want to look at the Canlin detector, I'll select my Canlin detector, and then this is asking, do we want to calculate the geoneutrino flux, or are we just testing a couple of different things? Do we not want to go through the whole calculation? But yes, we want to do the whole calculation, and so we're going to check off this box. Please calculate geoneutrino flux. The next part that we see explains what the difference is between the detector near field versus far field. So because the strength of the geoneutrino signal, the strength of the geoneutrino signal is indirectly proportional to 1 over r squared, the distance from the detector, we have to have a good high-resolution model of the rocks and the geology around each detector. And this is just saying, what geometry do you want that to be in? Do you want that to be a circle around the detector, or do you want it to be some rectangular tiles? I'm going to go with the traditional method, which is rectangular tiles for this calculation that we're doing now. After that, as I said, we have to choose, we have to model the lithosphere for these calculations. So we have to choose which geophysical model we want to use and input. We have 4 different options currently programmed in Crust 1, Crust 2, Litho 1, and ECM 1. You can read all about them here, and you can see some figures for what they, the differences between them look like. I'm going to choose Litho 1.0 for this run through. I might recommend doing the latest one, which is ECM 1. Then we have a couple of more options and parameters to choose as we go through. We have different ways of calculating the deep crust, and you can read about those in these hyperlinked papers. And then last but not least, we have to select how many iterations we have to run. So this code is a Monte Carlo, a bootstrap method that is going to do different iterations, 1 to 10,000 different iterations, using different amounts of the physical parameters that you're putting in here, like uranium, thorium, the thickness of the crust. Now, why do we do that? It's because the distribution of heat-producing elements in Earth's crust is non-parametric, not easy to describe. So basically, through a Monte Carlo, we brute force look at all of the different options for the amounts of uranium and thorium and concentrations that can be here. And when you run thousands of iterations, you generally stabilize on a central value or a favored or preferred value for these amounts. However, because we don't want to be here for hours, I've just set this number to 15 to run right now. This is not a very robust model, but it's good enough for you to get an idea of what's going on while we go through this script and have this recording be reasonable. This portion here you'll see is optional. We can define and open a parallel pool on our computer. If you want to know more about parallel pools and parallel computing, you can click this link and read through. But what this does is it talks to our computer, our desktop, and it says, how many cores do you have available on your processor? And do you want to use more than 1 core at a time? So I could run these 15 calculations sequentially, and I can do 1, 2, 3, or I can make use of all of the hardware on my desktop, and I can use all 8 cores and run calculations in parallel, so a calculation on each core. Now, if you don't have the ability to run a parallel pool, or if you're doing this online where you're not connected directly to a desktop, you would uncheck this box. You don't want to start a parallel pool, and you would just set this to 1. But if you do have that option and you want your code to speed up, you can run a parallel pool, and you'll see I've set my pool size to 8. I have 8 cores on my CPU. And last but not least, what do you want to call your run? I just decided to call this Test Run 01. Please name it something informative so you remember what you were doing when you ran this. Down here is just the printout from before when I hit run, and it started to check if I had a parallel pool open on my computer. And you might have seen a pop-up in the bottom left corner that said that it was starting a parallel pool and connecting. That's what this is. And actually, this code ran faster than we did through it, but we're still going to review these variables and then see the results. The good part is most of what you have to change is going to be in that first section, and after that, there's only a couple more steps that you need to take, and the rest of this big long code is actually just descriptive text telling you what the calculations are doing and why, and giving you references and justification. So you can read through all of that at your own speed to understand. The good part is beyond this point, the beginning of step 2, there's only 2 more sections where we as users have to change input. Let me click on this and it'll skip me right down. 2, I have to define what I want my abundances to be for the heat-producing elements in the lithosphere, right? So we are generating the lithospheric model to subtract it from the total observed signal. I have to fill in the abundances of uranium, thorium, and potassium that I want to use for my different layers of the crust and lithosphere. So you'll see a layer for oceanic crust, a layer for upper continental crust, lithospheric mantle, sediment, and then you'll see it's a slightly different method for the middle and lower crust. Please note that when you fill in these abundances, the first number is going to be what you want your central value to be, maybe your mean or median abundance. And then your 2 consecutive values are going to be your positive and negative uncertainty. Also, please note the units that these are in, as most of these papers will list abundances of uranium and thorium in parts per million or parts per billion, but we're going to go with parts per million. So just make sure that you write your units in kilograms per kilogram. So if I am translating ppm, parts per million, to kilograms per kilogram, 1 part per million is 10 to the negative 6th power, right? So it's 1/1,000,000th. So just make sure you scale that correctly. Once you go through and fill all of these out, you'll get to the section of middle and lower continental crust. Now, this was actually one of the parameters that you could choose above. And if you want to discuss why we don't just fill in values for the middle and the lower crust, but we do a little bit extra calculation, please contact me. That was what most of my dissertation was on, and I would love to talk to you about it. Alas, though, we will just get to our last section where we have to change values. And this is the section that says mantle, geoneutrino signal, and style. Now, you might be thinking to yourself, wait a second. We said we want to figure out the mantle geoneutrino flux, so why are we inputting it and calculating it here? I thought that was the whole portion of this, was to subtract out the lithosphere from the total so that we could get the mantle. And that's very true. However, sometimes we want to run these calculations at hypothetical detector locations where the detectors haven't observed any signal yet, where they haven't been built yet. Or maybe there's other experiments that we want to test out and run. And in that case, what we want to do is we are going to generate a mantle signal here. If you want to do that, you'll check off this button and you'll check whether you want a layered mantle or homogeneous mantle, and you'll have to put in some a priori knowledge about the amount of uranium parts per billion in the mantle. So this is if you want to, as I said, do those calculations for a detector that hasn't observed any flux yet, or you're doing some other hypothetical experiment. It's still usually pretty informative to do, though, so I would go ahead and check that box if you have the time. It will make the code take a little bit longer because now you're also calculating the mantle. The rest of these sections are defining different constants that are used in the calculations and putting them into the code, such as the heat production per decays, the number of decays in a uranium-238 decay chain, antineutrino oscillation parameters, and so on. And you can read about where each of those come from, once again, in these papers linked here. If for some reason you don't have access or institutional access to these papers, please contact Bill McDonough. I am sure that he would be happy to give them to you, or you can contact me as well. There's a couple of last steps we do outside of the Monte Carlo loop, including setting up a calculation to convert from measured flux into TNU. So the measured flux is going to be in, oh goodness, Bill will be disappointed. What is it? Centimeters per second squared, or something like that. I apologize, it's been years since I've done this. And to TNU, terrestrial neutrino units. And we just have some information about our model output to the command window as we run through. So you'll see here that my script is actually done running in this time it took to get here, and you won't see these outputs in this monotype code until your script is actually done and running, right? So it'll appear more like this with the outputs gone. All right, almost done. We are at step 5, the flux calculation. And this is the portion where all the good stuff happens, where the geoneutrino flux is calculated. There is a code behind this that you can dig into if you want to. You can see there's a par4 Monte Carlo loop. So if you are familiar with MATLAB or coding languages, definitely dig into this code and look through. If not, just let it run. What happens afterwards is that the data, the results from this code will just get restructured slightly into a more digestible format, and it'll provide you some summary statistics. As you can see, it took about two minutes to run that. And then, of course, we want to save our data. Now, these angry orange text here is once again just on my screen because of how I have it set up. You might not see these. These are warnings. Don't worry. If you see these, everything still works fine. And then we also have it set up so that all of your information will also print to a .txt, a text file, in case you're running this on a remote cluster and you want to retrieve it later and remember what you did. All right, now we're almost at the end. The last portion of this just visualizes the results, and this is a work in progress section. We are trying to figure out the best way to get this information visualized and to make it helpful for you. So we only have a couple of visuals here, and we would love to hear back from you about what sort of plots, charts, tables would be helpful for viewing your results. Here's just an example histogram of, lithospheric heat production distribution from our calculation. We also have, I put in another example, one of the mass of the lithosphere. If these numbers seem inaccurate to you, they probably are, because we only ran 15 iterations instead of 15,000. Now, if I swap back to the code, just one last bit for those of you who are more interested in the coding side of it, you'll see I have a red exclamation point, and that means that I have encountered an error. So in MATLAB, if I have this error, I can click on it, and it will show me where the error is, and I can scroll on down and scroll past the code and see where it might be. You might have these orange little warning labels where those aren't errors themselves, but MATLAB is suggesting perhaps a better way to word this code. Like I said, if you are just running the software, it should run through no problem. If you are interested in more of these errors, you can talk to me if you want to help us go through and develop this. All right, so that should be just about it. Our code has run through. I'm going to pop my panel out on the side back, and you'll see that we saved some results from below. We have, our Camland flux results, and we saved some files as well. And you can always load these back in if you want to work on your results after you've closed out the program. Couple of last notes. There are a few extra scripts on the side, which we have not gone through yet. There is a GEONU form, which was the short calculator form, which is exactly the same as the full script, except for you'll see there's a lot less rich text, and it's just really the options for selecting your different parameters and then going. This version, it was just finished recently, and it's for if you already know what's going on in the other code and you just want to do a quick calculation. A couple of one last option actually, is separate from the geoneutrino flux calculations total, but I have it packaged in here because I think it might be useful. So if you are interested in seeing the graphs that have on the y-axis the physics signal, the total geoneutrino flux, and on the y-axis the lithospheric signal, and you want to test numbers from different papers, you can do that here. Where, for instance, I have fields that you can fill in slots for instance, the Camland signal, the Borexino signal, and uncertainty, for the total signal in the lithosphere, and it'll do a little bit of calculation for you where it'll tell you the uncertainty, and it'll tell you roughly, given different detector measurements, what is the radiogenic power in both bulk silicate earth. So you can test out different detector signals here as well. What this does is it runs a multivariate regression to find out what this best fit line is through these points while taking in uncertainty on both the x and the y axis. All right, I'm going to stop sharing my screen. Thank you for sticking with me through this video. That will be about it. If you have any questions, please contact us, contact Bill, contact myself. And we hope that you get to test out the software and find it useful. All right, thank you.